So I'll talk first about direct and indirect effects, then the interpretation of marginal impacts, and then something nobody talks about, as I mentioned, the spatial pattern of the multipliers. So direct and indirect effects. So what we're interested in, and the whole reason we do this spatial analysis, is we observe in many instances that there are spatial spillovers. The whole notion of agglomeration economies, those kinds of things, the Jane Jacobs, you know, the whole thing that there is something more out of being in physical proximity than there is the whole is more than the sum of the parts. And that implies a multiplier effect. So if there is a multiplier effect, then what I do in one location, and what I mean by what I do is change the values of my variables on the right-hand side, the x variable. What I do to an x variable in one location affects the dependent variable, the y variable, not only in that location, but also in other locations. And that's what makes it interesting. So if you do place-based policies, people don't like to talk about that too much anymore, but you know, in the Obama administration, that was a big deal. The effect of these policies is not just local, but it spills over if there is spatial interaction. If there's no spatial interaction, it doesn't spill over. So the more spatial interaction there is, the more value for your money you get, so to speak. The larger the multiplier will be. Well, the multiplier is all about, that's what all policy is about. Spend $1 and you get more than $1 back. If you didn't, then you wouldn't spend $1, right? That's bad policy. So you want to have these multiplier effects. And so with these spatial models, what we're able to do is actually get a very fine-grained view of what is going on when we change something in a particular location. You know, for example, you do an infrastructure improvement in one neighborhood. Does that just impact that neighborhood, let's say in higher quality of living, or does it also impact the adjoining neighborhoods if there are spillover effects, right? And that's something that with these models we can quantify, measure. Is it there to begin with? That would be the difference between a lag model and an error model. Error model, no spillovers. Lag model, yes. And then how large is it and how far does it go? So the strength and the spatial range of the multiplier, these are really important concepts. Okay, as we saw the first time, regression coefficients in a linear model, very easy to interpret. It is on average what happens to the dependent variable. So if you have crime as a function of unemployment, if your unemployment level changes, what does that do on average to crime? That's, in technical terms, the conditional expectation. So the impact of a change in x, 1x or multiple x's, on y, that is the interpretation of the regression coefficient. In a linear regression, that is beta. So the total effect is beta times delta x. We have x beta, we change, you know, and unemployment. What does that do to y? It is the change multiplied by the regression coefficient. So the reason this is important is this is a different perspective from significance. So we're trained, and I think overtrained, in thinking about significance and p-values and all that stuff. So you do a regression, you look at the betas. Essentially what significance is about is this beta different from 0? Okay. It doesn't say anything about how big is the beta, how important is the beta, what does this beta do? you can have a significant beta that when you change your x, it basically does very little to your y. You know, if your beta is 0.002, but it's estimated with very high precision, so in a significant sense, you say, oh yeah, it's significant. It's not zero, but it's only 0.002. So if your x variable is something where you put in money, you only get not 2 cents on the dollar, but 2 cents on $1,000 or whatever it is, right? I can't think straight, but you just multiply that. And so that is a different way of looking at regressions. It's not thinking about, is it zero or not, but it's thinking about, what does this do if I change the right-hand side? What does it do to my left-hand side? Which is a notion of impact. Now, in a standard linear regression, it doesn't matter that much because they're basically the same, right? And there's no spatial effect. In a spatial regression, they're no longer constant over space, and that's the big difference. So in an SLX model, which is the simplest one, what happens when we change x, right? And typically, I'll get back to this in a few minutes, typically this is looked at with a uniform change in x. So what happens if there's 1% less unemployment everywhere? So delta x is the same everywhere. You might as well call it 1. It doesn't matter. A unit change in x. So we just talked about this a few minutes ago. If all these x's are the same in all locations, what are all the wx's? If delta x is 1 everywhere, what is w delta x? Also 1. With row standardized weights, it's the same thing we talked about with the constant term in the SLX model, right? So the changes, the overall changes in the overall effect of a change delta x is this beta plus gamma, right? And in our terminology, this gets a little confusing. I'll get back to this later. The effect of the immediate change, beta, is called the direct effect. And the effect in the neighbors is called the indirect effect. So the indirect effect is just gamma. The direct effect is just beta. In the SLX model, it's very easy to separate out the effect of a change in x in your location. So you paint your house value goes up. Okay? Your neighbors also paint their house. As a result of that, your house value goes up even more. By how much? By gamma. But then the neighbors of the neighbors, whether they paint their house or not, doesn't matter. It's only the immediate neighbors. Okay? So in the classic SLX model, and we talk about that in a couple of lectures, is just row standardized weights. There's nothing magic. The effect is always gamma. In nonlinear SLX models, it could be, for example, when we use kernel weights, it could be less or more than gamma. Okay. So then you have to actually calculate it, what it is. And we'll do that in a few minutes. Okay. Now to the spatial lag model. So this is where it gets interesting. In the spatial lag model, the effect of a change in the explanatory variables, the x's, on y is found in the reduced form. Since it is the average, the expected value, we don't have to worry about the error terms. It washes out. On average, the error terms are 0. So the only part that matters is this first part, So we have our inverse that we always have. We have the change in x, and we have beta. We've seen that we can write this inverse as a series of powers. So then, as a result, the effect of a change of x is for the location itself, for the first order neighbors, for the second order neighbors, and so on. The overall effect is more than beta, and that's the spatial multiplier. And then it's a little tricky to separate out direct effects from indirect effects. And the reason for that is that the change in the location itself, remember, I am my neighbor's neighbor. So there is a bouncing back of effects. And at the end of the day, when all this bouncing is done, I actually come out ahead with a higher value than beta. That is called a direct effect. So the direct effect in a spatial lag model is more than beta. In a standard regression model, and even in an SLX model, is just beta. And then the indirect effect is everything else. And that's kind of complicated. The way we do this is it's easy to figure out what the total multiplier is. So then the total effect is this multiplier here, 1 over 1 minus rho, multiplied by beta. That's the total effect. The direct effect is actually relatively straightforward to calculate. Then the difference, we call it indirect effect. So everything is very nicely split out. If you're only concerned with the overall effect, you don't want to know about this split. Total effect, very easy to calculate. But if you want to know what exactly is, in a sense, internal and what is external, then you can split them up in direct and indirect effects. In the spatial Durbin model, total effect is the same. The only thing that's different is how we divvy it up between direct and indirect effects. And here it gets a little complicated because in some literature, the direct effect includes Wx. And then I personally think that gets very confusing because in the SLX model, we call Wx an indirect effect. And so in the spatial lag model, we call it an indirect effect. Here in some literature, it's also called direct effect. And, to some extent, I can see that in a very strict sense. It's kind of the bouncing back on the neighbors. I personally prefer to just call that indirect effect. So it's just a different way of allocating the overall effect to direct and indirect. But otherwise, it's the exact same rationale. So that's overall. Now, what is the effect at the margin? And there's 3 kinds of effects. Okay. And the notation gets a little complicated, but just look at it carefully. The direct effect is the effect of the change of a variable in a location on the dependent variable at that location. So change in unemployment at location I on crime at location I. That's the direct effect. The effect of neighbors is the effect of changes in a variable at your neighbor location on your dependent variable. So that's changes in the paint of my neighbor's house on my house price. The first one is change in the paint in my house on my house. This is change in my neighbor's painting on my price. And then the last one is what my painting does to my neighbor's price. There's the effect on neighbors. And to get all this calculated, the critical role, obviously, from the reduced form is this inverse matrix. And this inverse matrix has two things in it. As I mentioned, the strength of the interaction, which is rho, and then the range of the interaction, which follows from the structure of W. Nothing else. There's no parameters in W. Whatever you use for W has a major effect on the range of interaction. How strong the interaction is depends on a coefficient on rho, but not the range. I mean, the range is a combination of the two. So then the math gets a little complicated. We have one of my favorite things, partial derivatives of matrices. At least it's not a determinant or an inverse of a matrix. That's real fun. But conceptually, this shows you what is the effect on y in location 1 of a change in x in location 1. What is the effect of y on y in location 1 of a change of x in location 2? So as we go along the row, that's the effect of the neighbors. The neighbor 2, neighbor 3, neighbor n on 1, right? If we go down the column, that's the effect on the neighbors. So this is 2 on 2, but this is 2 on 1. And this is 2 on 3, 2 on n. So row is effect of the neighbors on me. Column is the effect of me on the neighbors. And then you can compute these things. Once you have that matrix, you're in business. And in an article in 2000, actually in their book, 2009, Lesage and Pace lay out these summary measures, which are very quick measures of the impact. And you can compute the average direct impact. And if you look at this matrix again, the average direct impact will come from these elements on the diagonal. So you add all these up, and then you divide by the number of observations. That's pretty much what this expression does. And the average total impact sums everything in the matrix and divides it up. The multiplier is always 1 times over 1 minus rho. So this looks a little bit more complicated, but it's basically this thing is a vector of ones, a row vector. This is a column vector of ones. So if you work out the matrix algebra, this is nothing but summing all the elements in the matrix and then taking the average. So they use these average direct impact, ADI and ATI, and then the indirect impacts are the difference. So the ADI is easy to compute, ATI is easy to compute, AII is not so easy to compute, but it's easy as the difference between the two because it's one or the other. Can't be anything else. Right? And then these are summaries. We can also look at the impact for each specific observation. And this is described, but I've rarely seen it actually computed. And there's different notations. I like the effect of neighbors on me, that's the row. The effect of me on the neighbors is the column. So this is nothing but, again, using these vectors of ones, kind of a complicated way of writing out what is going on here. But essentially, it's nothing but a sum of the rows or a sum of the columns and taking out the diagonal elements, because those are the direct effects. So for any observation, you can, once you have this matrix, you can look at the row elements and you take out the diagonal, you add up the row elements, that gives the effect of all the neighbors on you. If you do this with the column elements, that gives the effect that a change in U has on all the neighbors. So from a policy perspective, at least from my point of view, that's the most important one. If you're going to change something in a neighborhood, what is the overall effect of that change on all the neighborhoods in the system? And the interesting thing, which is masked by these averages, is that it's not the same everywhere. It's actually very different. And that spatial footprint of the impact measures is something that I find very interesting, but I must be the only one because nobody ever does it. Okay. But you will be able to do it in the notebooks. Okay. Then, since everything is random, it's very difficult to actually interpret whether these impacts are significant. And there's kind of a technical literature that tries to figure out basically standard errors for these impact measures. Yeah, I think it's more important to do simulation if you're gonna get a sense of what is going on. So in a nutshell, the assumption of a uniform change, I think, is unrealistic. So all this stuff with the averages, it's useful. They're very useful shortcuts, but they wash a lot of interesting detail away. And especially thinking delta X is uniform everywhere, that doesn't happen, okay? No policy gives an equal amount to all locations. That just doesn't happen. And then the nice thing, though, is that if you have this reduced form, if you have this matrix inverse, then you can do anything you want. You can put a particular profile. Let's say you only invest in West Virginia. What does that do to the surrounding states? And you can figure it out. You just plug in the numbers and run the simulation. Okay. What if you give differential amounts to different counties in a state? What is the overall effect? And then if you know the differential effect of each location on the neighbors, you could put more money or less money, depending on your perspective, in the locations that have the most multiplier effect. Okay. If you want to have an equal bang for the buck, then you don't have to give that location the same amount of money because it gets more spillover effects. And it all depends how you approach it. The interesting part is to realize this is not uniform. And I show you in a second. Okay. Spatial patterns of multipliers. As I mentioned, even with a constant change in X, I didn't mention this actually, but the impacts of the neighbors, the row effect and the column effect, are not the same. They're not constant over space, or some are constant and others are not. Now, interesting enough, the averages mask this, because if you do the average by row or by column, you get the same number. So on average, they're the same, but the spatial distribution is not the same. And a lot of the spatial distribution, actually almost all of it, is driven by the network structure of the spatial weights. And how do you know the network structure of the spatial weights? This is where GeoDa comes in. In fact, you can do it in PySAL as well, but it's a bit of a pain. So in GeoDa, for any weight matrix, you can save the cardinality of neighbors. That's the number of neighbors. So if you have a weights matrix, it basically tells you for each location, what are the neighbors, right? Some locations have 3 neighbors in this Alabama or Mississippi example, but some have 9 neighbors. It's not the same. And in GeoDa, you can save this, you can map it. This is a neighbor cardinality map. So it's a map that shows for each color how many neighbors that location has. And it's, these numbers are discrete, so it becomes a categorical map. Doesn't have to be, but it's easier to see it that way. And then superimposed on that, we draw the network structure, the graph of the neighbor connections. So in the weights matrix, this one here in the middle has 9 neighbors. That means there should be 9 lines connecting that centroid with the centroid of the neighbors based on contiguity. See, there's some weird stuff here. These touch. You can't see it on the map, but they actually do touch in the underlying GIS. So the red one becomes a neighbor of this one, even though it doesn't seem quite that way, right? This network structure shows, I mean, some of you have done network analysis or graph theory. You know, there's all kinds of measures of connectedness for a graph, which, you know, how many in connections there are versus out connections. And that gives you a sense of where are the major players in the network. So where are the places where if you make the change, you have the biggest impact? Or I think I mentioned this before, the other way around, if you take them out, how do you break the network the most? And these are important characteristics of network structures and actually used in military applications, in emergency applications. You know, if the bridges break, which bridge do you need to fix first to establish the most connections in the network? That's a very critical thing in emergency management. And in marketing, you know, who are the influencers? You know, who do you get to on TikTok to reach the most people? And how does that structure in the network, not just who do they reach, but who do the ones they reach? Because then you get a multiplier effect. You know, and so this is all the same math. Graph theory is critically important in this. But this is just a simple explanation. And so we're going to exploit this by computing the impacts. Simple one, SLX models. So the SLX model, if you have a contiguity weight, then the impacts of the neighbors are from W, the W, X, change in X, times the gamma coefficient, right? This is just simple example, just one variable, one X variable, a given gamma coefficient. So what do you see here? The mean is the same. The effect of the neighbors, that's the row effect, is all one. You know, there's no variance. See, E minus 17, that's 0. But the effect on the neighbors is not the same everywhere. There's quite a bit of variability. In fact, it goes from 0.55 or 0.56 basically to a maximum of 1.67. So there's quite a difference. Where does that difference come from? It comes from the weight structure. Okay. And specifically, the column sums of the weights. If we have kernel weights, ignore this one here, then again, the averages are the same, but they're more than one for this particular kernel function. And both the row structure and the column structure are different. And then we can map this for the simple SLX model. The effect of the neighbors, as we saw, is 1, so that's not a useful map. It's all the same. But the effect on the neighbors shows you that there's quite a difference, and shows you specifically that these well-connected, this was the most connected ones, these well-connected ones have the most bang for the buck. And these less connected ones, typically near the boundary, have much less effect on their neighbors.
This map, right? Like there's some in the bottom left, there's one that has 3, maybe 4 connections, but it's
See,
seems to be more.
it's not just who you're connected to, it's who they're connected to. So in the network structure, if you're connected to one that has itself many more connections, then it moves through the system. If you're connected to one that has very few connections, then it doesn't move through the system, right? If you're on TikTok and your aunt watches you and she doesn't talk to anybody, that doesn't do you any good, right? But if some other TikToker watches you and starts talking about you, that does do you a lot of good. So it's not intuitive. Mathematically, it's totally tractable. So mathematically, if you go back to the weight structure, and especially to the inverse matrix, then you see what's going on, you know. And this is all I do here, and all you can do in a notebook is you get this inverse matrix, you do the row sums, you do the column sums, and then you map them. And you see what shakes out. And as you say, it's not necessarily what you expect, because it's not just first order effects, it's higher order effects. So let me go through this quickly so you can see this. Nonlinear SLX, we haven't really talked about. Here's a spatial lag model. That's the one that's most interesting, because direct effects, indirect effects, these are the same. The sum of this and this are the total effects. So the parameter I use is 0.5. The spatial imprint is very different. One thing that's very interesting, and to me it was a bit of a surprise, but then when you start thinking about it, it's actually not a surprise, is that the direct effect map and the indirect effect map are the exact flip of each other. So what has, and it's understandable when you think of the total effect as fixed. So the total effect is fixed. So with a uniform change in X, the total effect is always the same. And that has to be divvied up between direct and indirect. So if direct is larger, then indirect will be smaller, and vice versa. So these two are the exact flip of each other, and then the effect on the neighbors comes here. And again, as you say, it's not immediately straightforward, but if you look at the, well, if you look at the inverse matrix, you see it. But if you look at the network connections, not just with the immediate neighbors, but with the neighbors of the neighbors and so on, you can see which ones are the drivers. So in this particular case, these are the central counties, and you see that the counties on the edge don't have a lot of effect on the neighbors in the full system. It's on the full system, right? So there's a notebook where you can play around with this and try this for different parameter values and different weights matrices.